Hey team, I want to spend some time talking a little bit about portfolio analysis and optimizing portfolios in this video. So we've talked about in class how to essentially assemble a portfolio by using the Alpaca API, pulling down various different companies' current tickers. So we'll be using that as well as a Monte Carlo analysis in order to work with what we will refer to as the efficient frontier. And additionally, we'll do a little bit of correlation study to optimize the idiosyncratic risk of our portfolio as well. So first off, I want to talk a little bit about the efficient frontier. So let's go ahead and do a really quick Google search about that. I'm fairly certain I have one in here, but it'll be nice to do it live. So efficient frontier, this is probably a good image right here. It is. So let's go ahead and open that. So efficient frontier. Effectively, what we're looking at is a chart with the risk on the x-axis and the return on the y-axis. And what we're essentially looking at is as I change the mixture of the components of a portfolio comprised of asset B A and asset B, I can modify the risk of that portfolio as well as the return metrics of that portfolio. Obviously, with more risk, I should be able to get more reward, but what are the more intermediate values? So we're doing this only with 2 assets right now. The example we're going to do in just a second, we're going to have quite a few more. But effectively, what the efficient frontier is useful for telling us is that, 1, if we alter the mixtures of the assets that are in our portfolio, we can modify our risk return metrics. 2, that for any given portfolio, there is a minimum variance, that is to say a minimum amount of risk that that portfolio can take on, as well as a maximum return, that is to say that a maximum return that the portfolio can take on. We can additionally take on any of the values that are inside of this region between A and B. These are all potential portfolios we could create here as well. However, none of them are efficient. That is to say that only the portfolios that are on this efficient frontier do a good job of maximizing the amount of return for a specific amount of risk, or minimizing the risk for a specific amount of return. So this is why we like efficient frontier. It allows us to effectively optimize the actual weightings of the portfolio so that we can maximize the risk and return metrics of our portfolio. So let's go ahead and take a look at an example in some code. Again, we'll walk through a couple of different things here, but first off, let's go ahead and create our analysis.py file. Excuse me, IPyNB, not analysis.py. And we'll go ahead and open this in VS Code. I am going to blow that up to full screen. And it looks like we can't find that file. That's interesting. Let's try that again. And we'll get rid of this old window here. There we go. So empty notebook, let's go ahead and dive in here. So first off, I'm going to import pandas as PD. We're definitely going to be taking advantage of Alpaca, so I'm going to from alpaca trade API.rest, I want to import both the REST object as well as the time frame object. And I'm going to also import the random library, which is what we're going to use in order to produce our Monte Carlo simulation. So we'll definitely need all 3 of those to get started here. Before we get too deep into actually writing some code, we do want to go ahead and build a roadmap for ourselves. So first off, we're going to need to do a data ingestion. That is to say, to bring in the data from the Alpaca API. We'll then move on to actually creating a correlation study of our portfolio constituents. This is really useful, again, for minimizing our idiosyncratic risk and helpful for being able to identify potential places where we could take certain stocks out of our portfolio and, again, continue to maximize our return while minimizing our risk. And then finally, we'll get into our efficient frontier Monte Carlo analysis. And this is, again, going to help us to see all of the different portfolios that we could create. I'm going to go ahead and create those as different markdown sections so that we can revisit them and move up and down quite easily throughout this analysis. So first off, I'm going to create my data ingestion step. Then I'm going to go ahead and create my correlation study. And finally, my efficient frontier, which if I could learn to spell, we'd be great. Efficient is spelled E-F-F-I-C-I-E-N-T. Efficient. All right, so let's go ahead and talk about data ingestion. Now, we want to create this portfolio. Again, I'm going to want to naturally name my variable something that makes sense. The first knee-jerk reaction is going to be, I want to call this list of company tickers a portfolio, but for the sake of something else that's going to come up later on, I'm actually going to instead call this variable companies. So what is companies? Companies is going to be a list of a bunch of different tickers that I'm going to use for my portfolio. This is based on my actual portfolio that I'm using right now. As you can see, there's quite a few different companies across quite a few different subsectors in software and in tech, but there's a couple of clean energy ones and a couple of ETFs as well. So a nice little mix of things, which we're going to optimize through this process. I'll then want to go ahead and start setting up Alpaca. So again, Alpaca is going to be first off initialized by instantiating a REST object. We've shown you in class where you need to use the os.getEnv method in order to grab your API keys. In my case, I've actually got those in my environmental variables. You can find that in another video. And because they're in my operating system's environmental variable, that is, we don't need to manually do that in this step. Alpaca will actually scan for those automatically, which is awesome and a little bit less work to write on this particular line. From there, I can do the actual starting to make API calls for our actual stock tickers. So as an example, we want to go ahead and use this Alpaca object, and we'll use get bars. I'm going to start it off with a simple example just to verify that it works. So we'll go ahead and just grab MDB. We're going to need to set up the time frame. So that's where that time frame object comes into play. We're going to do daily, and we're going to grab data for the last year. So what I'm going to do is put in my start date as 2020. Again, it's year, month, day. So 2020, we're going to do month, it's October, and today is the 29th. Reminder that Alpaca won't let you pull data for this specific day unless you're paying for a premium data service. So I'm going to do it on one day back, a year ago, and then my end is going to be for 2020, the 10th, the 28th of October yet again. And as always with Alpaca, we want to get our data back as an actual data frame, so we'll throw .df at the end of this function call. Going ahead and running that, we can see that we only got one day. I've totally made a mistake here on the endpoint. I'm going to do 2021. And now I have a full year's worth of data. That's awesome. I want to be able to do that for each of these companies, however. So I'm actually going to turn this into a function. Oops. We'll do def get close. And what I really care about is getting the closing column out of this. So I'll create a function called get close that accepts a ticker. I'm going to indent all of that so that the alpaca.getBars is a part of the actual function body. We'll pass the ticker as an argument to the getBars function. And then from the response, we want to make sure that we only grab the closing column. And with most functions, again, let's make sure that we're returning some value back. So I would expect to get from this function the closing column for a particular company. Let's go ahead and immediately test that with a get close on MongoDB. Looks like we're still in business, which is awesome. So again, I want to use this get close over all of these different companies. So we're going to loop over that list of companies, calling get close for each one, and receiving a series for each one of those different closing columns. When we're done, we want to be able to concatenate all of those together and produce a data frame with the closing values for each one of the companies as a column in our resulting data frame. So what I'll first do is for company in, for ticker is probably a better word, ticker in companies. I want to loop over calling get close on that ticker. And what do I want to do with the result that I get back? Well, I want to put that into a list. So instead of writing this as a traditional for loop, what I'm going to do instead is a list comprehension. And we'll do get close of the ticker for ticker in companies. I'll go ahead and store this as a variable. This will probably be called my closes. And again, if you need to do this in a more traditional way, using get close and doing something like creating an empty list for closes, and then in the body of your for loop, doing closes.append, that works just as well. So again, both of these are equivalent. I'm just taking a more shorthand approach to it. So for each one of those companies, I'm going to get back a year's worth of data. And at the end, what I'm going to have as closes is a list of series. That is to say that each of the values in my list, if I go to the first one, is a series. If I go to the second one, is a series for the next company, so on and so forth. Well, I don't necessarily want that to be a list of series. I want to convert that to a data frame. So what I'll do is a pd.concat of that list of series. So that'll be my entire closes. If you look at your result, you get a very, very long, gigantic series. That's not what we want. So instead, we're going to set the axis to be columns for, and that does need to be a string, our access to columns for a concatenation. And we can see that now we get closing columns for each one of our respective companies. And then I'm going to go ahead and do a variable assignment so that df becomes our data frame name. And then I want to also rename the columns. Instead of having close for each one of these, I want them to be their respective names. So we'll just use the list of company names that we created originally to reassign all those column values. So if I do a df.head, we can see that I now have an awesome data frame that contains all of these various different companies' closing values for the last year. You'll notice that some of these have NANs. These are companies that are fairly nascent. They've had an IPO in the last year. We'll probably end up dropping them as a part of our process of optimizing our portfolio, but definitely worth paying attention to at this point. So now that I have a data frame, I want to again talk about returns. So in order to accomplish that, I need to make sure that I'm doing a calculation for that. So we'll create my returns data frame by simply doing my df dot percent change. What this is going to do is calculate my percent change for each one of those rows. And we can see that returns effectively gives us our, whoops, that's one too many cells. My returns data frame is now a data frame full of my return values. So next we want to move into this correlation study. So we've got this really useful data frame that we can start doing all kinds of great calculations with. I want to know what are the actual correlations with our value. So, or excuse me, our correlations among our different stocks. So a quick way to do that, again, in pandas, is to do returns.core. And again, this is a completely not human readable data frame. All right, there's a couple of superhumans out there for whom this is going to be ultra helpful. I am not one of those superhumans for sure. So instead of just doing returns.core, what I'm going to do is create a variable called correlations that'll hold this data frame. And I'm going to bring in a completely new library. It'll be Seaborn, which I'm going to nickname to SNS. And we'll do an SNS.core, or excuse me, SNS.heatmap on our correlations in order to get this super awesome and colorful plot. Now, this is not super useful as is. We definitely want to be able to bring this up in size. So we're going to make a couple of additions to this particular cell. So the library we haven't talked about a whole heck of a lot yet, but it's called matplotlib.pyplot. And from there, we can import that as PLT. And the first thing I'm going to do with PLT is actually set the figure to have a fig size of a 10 by 10. So don't worry about what those units stand for. Just know that 10 by 10 is bigger than the default size of this heat map. Additionally, in the heat map, we'll notice that our scale goes from 0 to 1. Remember that correlation goes from -1 to +1. So we definitely want to make sure that we're setting our Vmin to -1, our Vmax to +1. And just as a really useful feature, we'll often turn our annotations to be true. Whoops, I apologize. It is not matplot, it is matplotlib. And is it not fig size? Interesting. What did I make a mistake with? Fig size is an argument, not a function. That equal sign is super important. So what's useful about this plot, there's a bunch of numbers here. So again, I would never, ever, ever use this in a presentation. But it's useful to be able to start picking out some really high correlations between our different various stocks. So I might do something like expand this just a little bit in the x-axis to make those numbers a little bit more legible. But we've got a lot of things to point out here. So there's a 0.092. That's actually really low. I'm happy about that. Looks like Enphase and Solar Edge, those are both semiconductor companies, have a really high correlation. So probably want to drop one of them. I'm probably going to go with keeping Enphase just out of personal deference for the stock and the company, but definitely something to keep an eye on. Looks like we've got Hack in here with a really high correlation with MongoDB. Hack is a cybersecurity firm, or excuse me, a cybersecurity ETF. And MongoDB is a firm that produces a very specific type of NoSQL database. I, again, am very keen on MongoDB. I also think that while Hack does have a higher level of safety, the returns probably aren't as high. So again, I'm making some judgment calls here just out of knee-jerk reaction for the sake of this video, but if I want to do a better job, I would most certainly sit down and actually look at the return and risk metrics for each one of these companies. It also looks like we've got a pretty high one for ARK and Square. That's going to be because Square is in the ARK ETF. In fact, I think it's one of the major constituent parts of it, so we'll probably drop one of those as well. And anything else that really stands out? I've got SSUS, which is another ETF with VGT. Both of them are pretty focused on tech. We can probably leave one of them. I'm going to go with SSUS because I can see that while there's another pretty high correlation across the board with several of these, if we take a look at VGT, we can see that there's even more things that it has really high correlation with. So I'll take VGT out and we'll roll with some of the other ones instead. So what is the data frame we were working with? That was returns. So we will probably come out with, or excuse me, we'll probably instead select returns. We're going to create a new data frame instead of ruining returns. That's what I'm trying to say, where we're going to drop several of our columns. So we're going to do returns dot drop columns equals, and let's go ahead and drop. We know VGT is going to be one of them. We also mentioned Solar Edge. Let's drop, we said SSUS. Nope, SSUS we're keeping because we're dropping VGT. Got it. We had between Square and ARK. That's a tough one. So I've got Square, looks like it has pretty high correlations with quite a few things. ARK also has decent correlation with a few areas. Just for right now, let's just go ahead and drop Square and leave ARK. And we said MongoDB with Hack. I'm probably going to drop Hack here. We'll be left with our resulting portfolio. So I'll call that portfolio returns, which we'll preview to make sure that we're still in the clear here. Awesome. So again, one of the important things to be able to do with regards to optimizing your portfolio is to be able to identify really high correlations between different stocks that are in that portfolio. You could get deeper into this by looking at the actual return and risk metrics to make a decision between the two different stocks that you are trying to evaluate. But you could also start doing things like using a network diagram to try to identify which stocks often are related to one another or interact in very specific ways. So there's a lot more depth to go into in that one if you really want to, but I do want to have a good high-level discussion about that. Finally, let's talk about our efficient frontier. Now, again, we've talked a little bit about Monte Carlo analysis. We're essentially coming up with random values in order to be able to evaluate a potential future pricing or potential future values that can be taken on by a somewhat random process. With Efficient Frontier, what we're going to be able to do is start to take a look at the potential values that an entire portfolio can take on and how to optimize that portfolio. First, we need to have a short discussion about how to actually generate some random weights for our portfolio. That is to say, what mixture of different companies do we actually want to utilize? So the first thing we need to know about is our portfolio returns and their actual shape. So we can see that there's 13 columns here. So that's going to be super helpful because in our next step, what we're going to do is generate a random set of 13 numbers. So we're going to use our list comprehension again. We'll do random.random. This is going to randomly generate a value between 0 and 1 for some w in range of 13. So don't worry about the w. It more or less is just a value that we're picking up, or that we're creating to temporarily exist so we can create this list. And we'll call this our pre-weight, and we'll see why in just a moment. So again, I've got a list of numbers that exist between 0 and 1. I'm going to take that pre-weight, and I'm going to do a calculation of the sum of those different weights. Oops, pre-weight. And the reason we're going to do that is, in our next step, we want to take our pre-weights and divide each one of those by the weight sum. So what this is going to do for us is we're going to normalize all of these values. That is to say, we're going to force the sum total of these values to add up to 1. So these are the proportional values we'll get afterwards. And the reason we're doing that is we want to have 100% be our total portfolio, with the actual weighting of our portfolio split up across those different randomly generated weights. So we'll go ahead and do w divided by weight sum for some w in pre-weight. Again, that w is just a made-up dummy variable. You can call it anything you like. And all it is just a stand-in for whichever value we happen to iterate over at that point in time. So if we take a look at weights now, we've got completely different numbers, but in total, they'll add up to 1. And to prove that, I can do sum of weights, and we'll get 1.0. So why does that matter? What are we going to do with weights? Well, let's say we have some value, or excuse me, some portfolio with an initial value of $10,000 in cash that we want to invest in various different stocks. Well, I could do a calculation where we effectively take our, and let me make sure that I am using the right variable names here. Yeah, so I'm going to do portfolio returns dot producted with my weights. So what is that doing? It's essentially saying for each one of the companies that are in this particular portfolio, I want you to take that company and multiply its values by the weights that are assigned for that company. So I'm going to take MongoDB and multiply it by 0.069. I'm going to take the NVIDIA and multiply those values by 0.127. So why are we doing that? Because what we're going to get at the end of this is the weighted values for a portfolio that has these sets of weights as its values for the allocation of the portfolio to each one of those stocks. So we'll call this, it's a good name for this variable. I've dot producted my portfolio returns with my weights, so we'll call these the weighted returns. We can then calculate some cumulative returns by effectively using that cumulative product notation we've seen earlier in class. So I'm going to take my portfolio returns plus 1, my weighted returns plus 1, and do a cumulative product with those values. And I can do a product between my initial value and my cumulative returns and plot that, and we're going to get this really cool plot that effectively shows us this is the value of our initial investment over a 1 year period, had we, at the beginning of that period in 2020, 2021 08, 2021 11 01. So we might not have had a full year's worth of data there. Where did we? Because we have a bunch of nans earlier in our values. So what we're going to do here is we're going to drop Duolingo, Hut, and Indie as well. And that leaves us with 10 columns. So we'll do range 10 here. We'll have 10 weights. And now we've got a different portfolio because now we have different random weights and we have a different allocation for each one of those stocks. So what's cool about this is as I rerun this random generation of my weights, you can see that this portfolio takes on, again, different values throughout that entire time period, just depending upon what weights have been assigned to these stocks. So what we should really care about are two things. One, how much money can we make? What's the high bar on the upper end of money making we can do here? The next question we want to ask is, how much risk is associated with that particular weighting? So this is where the efficient frontier analysis comes in. So I'm going to write this out and more or less walk through what's going on here. So first off, I'm going to have an empty data frame into which we're going to put our results for this process. So this will look very similar to the way that we could have done the list comprehension at the very beginning. We're going to essentially walk through a set of trials, generating new values along the way. So first off, I'm going to create a set of weights. We're going to want a column for the total return. We're going to want a column for the risk. And finally, we're going to want a column for our Sharpe ratio, which we're going to calculate as a part of our process here. We're going to set up an initial number of trials. Again, anytime you're doing Monte Carlo, try a few. Don't go really big until you have verified that your code works properly. Then, for each trial or each run in my trials, not in trials, but in range of trials, excuse me. We're going to do a couple of things. First off, we're going to do that exact same pre-weight, weight sum, and weight process over and over and over again at the beginning of each one of our trials. We're going to also set up our same initial, our weighted returns and our cumulative returns process as the next chunk. So again, what we're going to do here is set up of random weights, and then we're going to set up the weighted returns of the portfolio. From there, we'll move into a little bit of a new territory. We want to talk about calculating the risk of the given portfolio that we've just generated. So we have a portfolio of stocks. We've randomly weighted how much money we're going to put into each one of those different stocks. Let's talk about the overall risk of that portfolio. Well, to do that, you've got to calculate the standard deviation, but of what? Well, it's going to be the standard deviation of our weighted returns. What that standard deviation now represents is for that portfolio, how much risk is associated with the actual portfolio we've just generated. And then we want to calculate the total return. And that's going to be taking our last value out of our cumulative returns. So again, our cumulative returns being the total return over the entire course of the investment. So our cumulative return, it will just be that very last value. If you want to do other things like calculate your max drawdown or other methods, that's definitely where you're going to put, this is where you're going to place that formula in your process. From there, we're going to go ahead and talk about our result. Oops. So I'm going to append to this data frame that's called results. And I'm going to do results is equal to results.append. We're going to use these weights with the weights that we generated. We're going to need that entire list. And the reason we're going to need that entire list is when we go to do our analysis afterwards, we're going to want to know what allocations for each stock did we have. Next, we're going to talk about our total return, in which case we just need to put in our total return value. Calculated, just throwing it in. Next, we want to talk about our risk. Well, again, simple value that we've calculated there for the risk. And finally, we want to talk about the Sharpe ratio. Again, the Sharpe ratio simply being the total return divided by the risk. So we're in a pretty good place. Let me double check, make sure I didn't make any mistakes here before we start running this bad boy. Okay. So from here, at the end of our evaluation, we want to go ahead and do results.head to make sure everything's gone hunky-dory. And looks like we do have a mistake in here. Can only append a dictionary if ignore index equals true. So this error is pointing at my results.append. It's referring to this dictionary of new values I'm trying to append. We're going to add ignore index equals to true as the error message asks us to. And this gives us our new data frame. Our weights column, again, is full of lists. This is something that's not going to be useful or human readable until we get a little bit deeper in. We've got our total return, the return for that particular portfolio, the risk metric, the standard deviation of that portfolio, and the Sharpe ratio, the return to risk ratio. Ooh, interesting. So now that we know that works, let's go ahead and crank this to something a little bit bigger. We'll go ahead and do 1,000 portfolios. And what's cool about doing this entire process is now we have this results data frame in which we can plot some things. So let's take a look at results.plot. I can do kind equals a scatter diagram. So the reason we want to do a scatter is we want to set the X as the risk, the Y as the total return. And what that's going to allow us to see, ultimately, is this really interesting and weird shape. Huh, that's kind of weird. Maybe if we increase our trials, we'll get an even more interesting shape. And so as you continue to increase the number of trials, you'll eventually get a more and more and more filled in structure. And what I want you to be able to see is there's this limit that starts to appear in terms of your risk will never go below a certain point, and your return will never go above a certain point. That is our efficient frontier. Let's go ahead and add a couple more things to this plotting method in order to make it a little bit more, again, interesting. We'll use the sharp column in order to set up the colors for this particular plot. We will use a color map of crest, crest, not crust. I personally like crest for this type of thing because it's a nice smooth spectrum that doesn't go red to green and fairly easy to see what's going on. And I'll set my fig size to be something a little bit higher. Let's do like an 8x8 just to see if that works for us. Yeah, it does. So what you're seeing here is, again, it's this same shape that we were just looking at, but now we have a color spectrum where the increasing sharp ratio is equivalent to our darkening blue color. So as you're getting to this dark blue, you're seeing the edge of that efficient frontier. So why is this useful? Why do I care? Well, there's a lot you can do with this results data frame, given that you now have this plot. If I'm only caring about values, or that is to say portfolios, that give returns in excess of 2.4 times my original investment over the year, well, that's simply taking our results data frame, doing a hard bracket, and we're looking for, within the results data frame, rows where the Sharpe ratio is greater than 2.4. And voila, just like that, excuse me, not the Sharpe ratio, the total return. So I'm only concerned with total return greater than 2.4. So now you have a large variety of of portfolios that you could potentially use that give you a return of at least 2.4. Okay, of the things that have at least 2.4 return, do I want to just use any portfolio? No, I want to use the one that minimizes the amount of risk. So in terms of minimizing risk, we could do a sort values on the risk column. And by default, ascending is set to true. So this first row with the ID 1627, this would give me at least a 2.4 with the least amount of risk associated with that portfolio, with a Sharpe ratio of about 85. That's pretty cool. Now I can talk about, this is the portfolio I want, and this is why I want that portfolio. It allows me to get at least this minimum of return that I care about, while minimizing the risk that I care about. What if I just want to maximize my amount of return for the amount of risk that I'm taking? Well, I can simply look for my results, bracket the Sharpe ratio. Again, I'm going to do a sort values, but we're going to do it on the Sharpe ratio column. And we're going to set ascending equal to false. So I want this in descending order. The biggest Sharpe ratios will be at the top. No axis name Sharpe for the object type series. Oh, I don't want that hard bracket there. I want the entire data frame. So now I can see that there are quite a few really high Sharpe ratio portfolios. Let's go ahead and just take the .head here. And we can see that there's one with 101 Sharpe ratio. So it maximizes the risk for the amount, or excuse me, maximizes the return for the amount of risk that we're taking on. Well, although this has a good chunk less of, let's just take the first 5 of those as well. While this obviously has far less return than the corresponding high Sharpe ratio portfolio, high total return portfolio, it also comes with less risk than that high return portfolio. It maximizes that Sharpe ratio. So what can I do with this to actually turn this into my trading strategy? Well, essentially what we're going to do here is select the weights out of this particular row. So I do something like results.ilock bracket number 380. Here's that actual row of data. I specifically want the weights out of that row of data. Here's the weighting for that particular portfolio. We'll go ahead and save this as a variable, best weights. We'll then take, and actually let's keep displaying best weights. That's useful for what's coming next. Then we're going to use a command we probably haven't seen a whole heck of a lot of in class yet. We're going to, first off, actually, I need to grab from the results, not results, from the portfolio returns. I need to grab the list of columns that we used. And I want to convert that into a list. And we'll call this portfolio, or excuse me, yeah, portfolio names. And now we'll use the zip command to bring together these two different lists. They're going to get zipped up together. You'll see exactly what this looks like. It's really neat. So we're going to have our portfolio names, not returns, but names, with our best weights list. This is going to create a zip object. To get everything out of the list, the zip object at the same time, you use a list. And now what we have is a two-dimensional list of tuples. MongoDB should be 5% of my portfolio. NVIDIA should be 0.07% of my portfolio. ArcK should be 4%. Salesforce should be 20%. Palantir should be about 2%, so on and so forth. So what makes this incredibly useful is effectively I have gone from, I have an idea about a group of companies that I just want to invest together, that I like. They might be all in the same industry. They might be in wildly different industries. I've removed some of the idiosyncratic risk. I've de-risked it in terms of removing things that trend together. And then I have optimized, that is to say, maximized the amount of return for the amount of risk taken on by this portfolio by modifying the different weightings of equity in this portfolio. Definitely play around with this one, bring in your own companies, try out some different things with this. You're going to have a lot of fun. With that, I'll catch you guys in class.